Good morning. This is Vikram Jandhyala. I'm speaking from Seattle. I'm the chair of the Department of Electrical Engineering at the University of Washington, and also founder and chairman of a company, startup company Nimbic, which works on cloud computing for electronic design. Today I'm going to talk about cloud-based engineering computation and how we can scale engineering computations using cloud computers. I'd like to acknowledge my colleagues at the startup Nimbic as well as my students at the University of Washington for the work which I'm presenting here today. So before we look at simulation on the cloud, we need to define what we mean by the cloud and what kind of software runs on the cloud and what approaches are to scalable simulation. And here, when I say scalable simulation, I mean parallel simulation, that kind of simulation which you can parallelize on multiple cores or multiple machines. So there are a large class of engineering computations, for example, those which involve solving matrix systems, or those involve large finite element or partial differential equation. Here we're going to look at a couple of examples from electromagnetic simulation and electronic design automation. And I'll also talk about other challenges associated with trying to compute larger systems on the cloud, including security, how to scale even larger, and even things like how to do design and licensing, which are all challenges on the cloud. So when it comes to engineering simulation, of course, engineers have been very adept at taking algorithms and adapting them for very different computing architectures. Many years ago, we had the client-server model with the first mainframes. Then we had multi-core and many-core systems. We also had SIMD and multiple input MIMD machines. GPUs have now become popular. Computing clusters, the most popular being Beowulf, has been around for a long time. And then there have been more dedicated high-cost, high-performance computing, HPC and supercomputers. So where does cloud computing fit in all this, and why is there a scope for doing something new in cloud computing? So before we talk about why cloud computing is interesting, let's look at how to define cloud computing. So here is an example from Amazon Web Services. Amazon, being in Seattle, is one of the companies we work with very closely in terms of putting our cloud algorithms on AWS, which is Amazon Web Services. So on the left, you see a user who is connected to the internet through a standard internet portal. And then you go through SQS, which is a queuing system. So for example, if you have a set of programs to run, you can queue them. And these are then run on the squares which you see on the right, which is EC2. EC2 is the Amazon Scalable Computing Cloud, also called the Elastic Computing Cloud. And why it's called Elastic is depending on how many processors or how many computers you need for a given process, you can buy time on them by the hour. So you can either add more nodes or reduce nodes depending on what you want to do. And these are all linked to S3, which is the simple storage service, or this is a large area to store either memory or database or other things which you want to store for longer use, including your data associated with your computations. So again, so there's a user on the left, a sequencing method, a set of processors, and a storage system. The only difference between having this in-house is that everything on the right is now in the cloud, meaning it is now publicly accessible by you, but still secure. But it does not physically belong inside your intranet. So in terms of cloud computing, the first thing to realize is that this is really an on-demand computing resource. That is, you can requisition directly by the end user. Unlike IT-based systems where it may take a few weeks to generate new computers, to buy new computers, here you can buy by the minute or the hour. So that's the paradigm shift, where you can add or subtract resources depending on your needs. And it is virtually infinite in the sense that the size of these cluster farms or server farms are very large, so you can essentially get as many processors as you need depending on your how much you're willing to pay. Now, the cloud computing also comes along with a catalog of services. So it's not just the hardware, but also the services, which includes bandwidth, computing, storage, software platforms which are built on top of the hardware, and then eventually application software or software as a service as different vendors try to place their applications right on these cloud machines. The advantages for the provider is that, first of all, there's large economies of scale through the fact that you can put a lot of machines in these massive data structures, and so you can amortize the cost of, for example, cooling the systems in terms of power, in terms of maintenance, in terms of pulling out hardware and replacing hardware. So these economies of scale are similar to when you make computer chips. The fact that you can make chips so low cost is because you're making so many of them. So similarly here, very large data centers can have economies of scale which a small company may not have. And therefore, you also get higher resource utilization because you have a lot of users and you can multiplex or virtualize these workloads so that you're really using these computers all the time and they're not being inefficient in power usage. It's also a very simplified operation because all these centers are uniform. You use the same kind of machines, same kind of algorithms, same kind of software, and therefore it's very easy to switch out. It's like using one uniform resource throughout the entire data center. As far as the software developers go, there's advantages for them too. As long as you can exploit parallelism in software, you can get on-demand scalability. So that means if you can write good parallel code, you can requisition these machines and you can really get scalability. You can easily distribute a software and have version control instead of having different copies to be managed by different license schemes. A user of your software will automatically have the latest version available on the cloud, so you don't have to worry about managing different versions or outdated versions. Virtualization really, of course, happens not just on cloud, but it's very easy to do in the cloud, so you can manage multiple OSs and multiple streams of OSs at the same time. You can do a lot of usability and metric study because if people are running on the cloud, you can measure how many people are accessing your software and how often and for how long. So you get a lot of understanding of how your software is being used by people, which you would not be able to do if it was running internally in some customer site, for example. There's also the potential to disrupt in a good way license and revenue models. People tend to write software which is sold by either perpetual license or yearly license, but now you can think of pay per use, which is you pay by the minute or by the hour, and so this gives new license models and revenue generation models as well. The cloud market itself, you should take into account all the hardware. It's a very large market because it's all these high-cost data centers and all the software and services associated. So it's about 68 billion and growing at 16% and projected to be almost 150 billion by 2014. Of course, this is the entire market, which includes hardware as well as all the services. So if you think of the software part of this market, there are different buckets. So inside you can see infrastructure as a service. So this is the actual hardware itself. So for example, Microsoft Azure or Amazon EC2 is the actual infrastructure itself. Now building on that is the platform, which is letting other users write applications on top of the hardware. For example, the Google App Engine is an example. And this is a market which is growing very fast at 70% per year. And on top of that is the application layer or the software as a service. This is where you can buy applications by the hour or by the minute, depending on what licensing schemes are available, and use this on demand. So again, you have the hardware, the platform sitting on the hardware, and then the actual software which is written on top of the platform. Now, there's a slight difference here which I want to mention between hosted software and scalable software. Hosted software simply means it's running on the cloud, and it may or may not scale. It may scale with some need. For example, web services is a great example. As more and more people try to access webs, if it's a well-written web server, automatically you generate copies of that web server on different machines so that you can handle larger demands. And similarly, database access is also the same. However, scalable software is that which comes from the scientific computing community, which takes advantage of either fine or coarse level parallelization, meaning parallelization at the level of very fine mathematics and computation using multi-core or multiple CPUs. And also it exploits the fact that you can get low-cost, on-demand, scalable clusters, not just single nodes, but machines which are tied together with fast interconnect. Okay, so that's really the difference between hosted, which is just running on the cloud, and scalable, which is you're really trying to parallelize your simulation on the cloud. So an example of engineering computations which I want to give is the field of electronic design automation. So as a market, this is about a $5 billion market, which is dominated by 4 players: Synopsys, Cadence, Mentor, and Magma. Now, all of these companies rely heavily on scientific computing algorithms, whether it's place and route, whether it's matrix computation, circuit simulation, and so on. So there are lots of scientific computing algorithms running for these underlying software. For many of these, parallelization is desirable. So, for example, if you want to do circuit synthesis, if you can do this in parallel, it will speed up your synthesis step. But not all tools which are electronic design are scalable. One example, challenging example, is the SPICE core engine, which is a time-stepping matrix, sparse matrix method with a nonlinear path based on transistors. And it's very difficult to parallelize this. Many companies have tried, but you've not yet got efficient parallelization. On the other hand, if you rerun problems for different designs, for example, so for example, if you have a circuit and you change some resistor values in rerun, that essentially is running the same simulation with slightly different values. That you can do completely in parallel very easily, or so-called embarrassingly parallel. So example of this is Monte Carlo, where you're trying to run many simulations. This is very easy application for the cloud. So depending on what EDA application you're doing, the cloud may or may not be the best suited for this application. But it's a large market, and in many cases speed is required, and therefore cloud is something which is which you'd like to use for this area. So in terms of taking these electronic design automation or EDA tools to the cloud, there are certain challenges. First of all is scalability. You want to parallelize, you want to get more speed. At the same time, you want to use all the memory which is available, which could be distributed memory. So if you have a large matrix, it may be sitting on multiple machines, and you want to make sure you can work with that matrix in efficient time. And bandwidth is another concern. If you have a lot of data being transferred back and forth, that will slow down, obviously, your overall time to get the result. So bandwidth is equally challenging. Security is interesting because there's a perception that the cloud is somehow less secure than any given intranet, although companies like Amazon and Microsoft spend a lot of effort making sure their data centers are very secure. So it's partially a real problem, and partially it's a perception. That is, data during transit from your machine to the cloud, is it secure? And secondly, once you are on the cloud, how secure is that computation? So that's a challenge to be addressed. Another is reliability. If you're writing code which is running on multiple machines, since you are running on a large number of machines, there is a finite probability that any one given machine will fail. So how do you ensure you write software which continues to work and you don't have to restart your entire algorithm? That's another challenge. And then there are other which are sort of software challenges. For example, interoperability. If you're putting many tools on the cloud, which are all part of some design flow or tool flow, they all have to work together. If you have some 3D rendering, for example, now this is being rendered on the cloud. So how do you make sure that latency is not too high and you can still use this? And finally, licensing, which is still an open problem, which is the way licensing is done. Many of you will know a company called FlexLM, which does licensing, which essentially ties you to a node or to a floating license on a computer or on a network. Now you want to license by the hour or by the minute, and it depends on how many cores you have as well. So your pricing and your licensing is still to be figured out when you have multiple machines which are running only for a short time, and after which you want to turn your entire application off. So is EDA, electronic design, a good example for engineering computation on the cloud? And the argument is yes, because first of all, EDA is very spiky. What that means is when you're designing a new chip, for example, very early on you do a lot of small tests for different parts of the chip. Once you're ready to tape out the chip, you do a very late stage verification, which is you simulate the entire system. So these are two very different kinds of simulations. In the first instance, you're running many small simulations. In the later instance, you're running one very large simulation which requires a lot of memory and a lot of computing. So the usage is spiky, goes from small to large, so it spikes at certain stages. And you do use a large number of resources. Very often, semiconductor companies use a lot of in-house compute farms, for example, Intel or Texas Instruments. Many of these applications are parallelizable, either partially, like SPICE simulation, or fully, like Monte Carlo. And of course, another thing to realize is that standard licenses for engineering software are very expensive if you buy by the year or by the perpetual license, because they're often not used every time. They're not used all the time. So if you can pay by the second or by the hour or by the minute, that's something that would be useful. But it is difficult for large companies to change their model because they are built on having very large in-house compute farms. So a very large company, a semiconductor company, will not want to put its IP or its data on a public cloud. So that's also a challenge to overcome. So we look at the first three. In fact, we'll probably have time to look at the first two, scalability and a little bit on security for electronic design, which is an example of engineering computation. So some examples within electronic design: electromagnetic simulation, which is really solving a very large system of Maxwell's equations, is a very common engineering computation, very similar to things which you do in other branches of engineering, mechanical, civil, chemical engineering, where you have finite element. So in the electromagnetic world for electronics, you do things like signal and power simulation, electromagnetic interference, EMI, which is becoming very important now with hybrid vehicles. That's an area where EMI has become very important. And you also do more standard parasitic extraction or analog design, for example, designing inductors on chip or designing packages and boards. So these are examples of how electromagnetic simulation is used on the cloud. So one thing we have to note is that we are not running on a high-performance computing cluster or an HPC cluster. And why is that? What's the difference? So if you look at the red block that's on the left, that's supercomputer. They have very large scale, of course. You have many, many thousands of nodes, and they're oriented towards specific applications. For example, optimized code written in C or Fortran runs on these computers, on these supercomputers. On the other hand, you have the cloud, which is the light blue on the right, which also has very large scale. They can be very small and go all the way, almost as big as supercomputers, but they tend to use more services. They have platforms, they have software as a service, they have a lot more libraries and existing software to use than application-oriented distributed systems. So how can we take advantage of that in the cloud? And also in between our grid computing, which is sort of a hybrid between supercomputers and clouds. On the bottom left are clusters. These are typically lower cost, smaller scientific computing clusters. So the cloud is large scale, not as large scale as the top supercomputers, but certainly allows you to do a large number of computations in parallel. The kind of parallelization that you can do on the cloud is also interesting. So the most standard one is multi-threading on the top left, which is really trying to do a parallel simulation across cores sitting on the same chip. So if for those of you who use libraries, this is OpenMP is a very common library used here, where you have one shared memory, which is shared by multiple cores, for example, a 4-core or an 8-core chip. The second kind of parallelization is on the right is MPI, which is message passing interface, which is if you have multiple machines, each with their own memory, so now you're sharing memory across, you have shared memory on each machine, but now you're distributing it across the machine, and you have connections between the left and the right machine which are not as fast as the ones between the CPUs on the same machine. So you have to be careful of the fact that you're now going to have slower computation or slower bandwidth, less bandwidth and slower transfer of data between the two machines. And that becomes MPI. Distributed is essentially the simplest. On the bottom left is really saying that you repeat the same task on multiple machines and then collect the data at the end. So that's, for example, Monte Carlo. You just run 2 copies of the software and then collect the data at the end. And interestingly, a lot of GPU paradigms are also showing up now on the cloud. So there is an interesting question, for example, NVIDIA has as to whether they should place a lot of their GPU hardware on the cloud. So that's still an unanswered question as to whether GPUs on the cloud are as useful as GPUs sitting on your desk. But interestingly, you have to hybridize CPU and GPU with languages such as CUDA, which is pushed by NVIDIA because GPUs are very fast. They have a lot of cores, but they tend to have small amount of memory. So you have to push data from the CPU onto GPU and back. And that sometimes tends to be the bottleneck. But in general, all of these 4 parallelization paradigms, multi-threading, message passing, distribution, or hybrid machines like CPU, GPU are available on the cloud. So we continue and we look at a very well-known law, which is called Amdahl's law, which says that if you have even a very well-designed parallel algorithm, as long as you have some sequential part in that algorithm, however small, eventually as you increase the number of cores, that sequential part will start to dominate and your speed up will hit a limit. So on the right, for example, you can see even if 95% of your code is parallel and only 5% is serial, as you increase the number of cores, you get a speed up which is 20, but it stays at 20 even if you have 65,000 processes as in the bottom right. And if you have only half your code parallelized, then the best speed up you can get is 2. And this is really the reason that why most software which is written for a few number of processes does not scale well when you try to just add number of cores. So for example, some as complicated as a word processor or Excel, Microsoft Excel does not run 4 times as faster if you have 4 cores, because there's a lot of serial access going on, a lot of serial algorithms. And this is what this slide is showing, that Amdahl's law is going to hit you, especially in the cloud. It's going to hit you early because when you pick different machines on the cloud, for example, Amazon has centers on the west and east coast of the United States and also in Japan. So if you pick nodes at random, these might be located very far from each other, which means a large delay and latency between the nodes. And that will hit you in terms of the amount of parallelization you can get. Also, you don't have high-speed backplane interconnects. If you think of high-performance computing supercomputers, the cost of the interconnect is almost the same as the cost of the hardware, meaning the chips themselves. So you spend a lot of effort on making very fast interconnect or connection between computers. This is not true on the cloud, which is catering to a more general market. And so you will see this kind of hit if you just try to parallelize, assuming that if you just assume that what you have is a scientific computing cluster, accept it from the cloud, you're going to hit this this limit in scalability very, very quickly. So you have to do something different or something slightly more complicated to try to get higher speed up. So I'm going to show you a toy example of what is done as an engineering computation. So this is a very commonly used engineering computation in lots of fields, whether it's mechanical, microfluidics, electromagnetics, civil engineering. It's the boundary element method, where basically you have a geometry, you break the geometry into patches. Typically these patches can be triangular as seen on the left, and then you try to find the interaction between every pair of patches. So the interaction in the electromagnetic sense is the electric field produced by current or charge sitting on these patches. And you can think of other interactions, for example, in fluidics, it's pressure and velocity. So what you get at the end of this is a basis function, meaning a charge sitting on one of the triangles. And what it does is it computes through the Green's function. So F is your source, G is the Green's function, and T is your test, or this is what is generating the field. So F you can think of as a source of current, and T is the electric field. Now you have to compute this for every pair of triangles. So if you have n triangles sitting on the green object, you have to do n squared computations. Again, n can be very large. For example, for a part of a package on a chip, n can be on the order of 10 million to 100 million. So if you're trying to do n squared computations, this is on the order of 100 million squared, okay, which is a very, very large number, 10 to the 16 operations. So very large number which will take you very large time to compute this matrix, this boundary element matrix. So what has happened in this field, boundary element field, is that there's a class of techniques called fast methods, and this has been around since the 1990s, which exploit the fact that when you're trying to solve a matrix which comes from boundary element, there's a lot of redundancy or a lot of physics in that matrix, that you can compress this matrix and give you very fast solution iterative solution to the system. So for example, what would take 2 days in conventional boundary element, it will take you 20 minutes with fast BEM. This is a well-known technique. Our group worked on it a few years ago. Many other groups have also worked on it. So this gives you large memory saving and a large time saving, even if you're running on one processor. So there's nothing parallel about this step yet. All it's letting you do is do very complicated problems. So on the bottom, what you see is a part of a cell phone board, and on the right you can see the kind of discretization, the number of triangles which you need to solve the electromagnetic problem. Once you have the electromagnetic problem, you can predict how much signal and power is going through lines, how much crosstalk there is between the digital part and the analog part, and so on. So it's a very powerful algorithm for signal integrity and power integrity. Now the question is, you can do this in many ways. One method we came up with is called Pilot, which is basically a way of doing singular value decomposition, which says that if you have a submatrix, you can write that submatrix as a product of a thin and tall matrix and a short and wide matrix. This is called the singular value decomposition. This works when the matrix is low rank, and there's a physical reason, there's an actual physical reason why this is true. Okay, so this holds for many cases, but the benefit is that the original matrix, which is shown on the top left, which had n squared elements, you can replace that with a very high accuracy representation with only n elements. So this gives you very large matrix compression. So when you're trying to run this in parallel, what you're trying to do is break the matrix which you're trying to solve into a set of low rank matrices, or a set of pieces which are low rank. So for example, you see this color map. The numbers of them tell you the rank of the matrix. So 7 on the top right is the rank of the yellow matrix, and so on. You want to do this compression in parallel and do it on different machines. So this is what can be done very easily on the cloud, because all you have to know is what the ranks are going to be. That is, if you know, you can load balance the computation. That is, you know how much work you're going to do to get the low rank compression, then you can just divide out the task amongst different processors or even different machines, and that's called static load balancing. If you're wrong on the rank, if the wrong rank turns out to be slightly different from what you expect, you have to do some dynamic correction or dynamic scheduling. But this lets you divide the compression of the matrix. And this is an example for boundary element, but you can think of the same methods for image processing and for biomedical imaging and so on as well. The same idea applies, which is you can compress different parts of your system in parallel on the cloud. Now, I mentioned earlier that you have different types of parallelizations, for example, OpenMP and MPI as well. So what this is showing is that you can hybridize OpenMP and MPI. So you can do part of the operation on a single machine, the part which requires a lot of computation and a lot of processing of bandwidth, and the parts which are not so tightly coupled, you do on separate machines. So you can hybridize this. So for example, in this case, you have a solve step. There are two kinds of solution steps you have. In one, you're trying to do a parallel matrix vector product, which means you're multiplying the matrix with the vector. This is a standard matrix problem. The other is you're trying to solve many different systems. So this could be Monte Carlo. So the same matrix, but different right-hand sides. So you're solving AX equals B, where A is a matrix, and you're solving for different B. So these solutions can be done completely independently, and this is where you can use something like SGE, which is Sun Grid Engine, which is basically just rerunning the same method on different machines. So it's a really distributed simulation. And finally, if you're running any engineering computation, typically you can solve in the frequency domain or in the time domain. The benefit of solving in frequency domain is, once again, you can solve at different frequencies. So in the mechanical sense, this could be different resonance frequencies. In a fluidic sense, this could be different oscillation frequencies of fluid. In electromagnetics, this could be different frequencies of propagation of the electromagnetic wave. So these can be solved just at different frequencies, completely in parallel, because they are independent solutions. And once again, you can easily do this on parallel machines independently. So what you're trying to do, if you put all this together, is that you're trying to have multiple levels of parallelism. So you notice that unlike the case where Amdahl's law is hitting you, you now have 4 different levels of parallelization. So you have the finest level, which is the yellow OpenMP. You then have MPI, the light green, which is multiple machines. And then you have 2 levels of distributed solution on top, one for frequency, one for right-hand side. And this lets you get around the challenges of Amdahl's law, even if you have computers which are connected with slow interconnect. That is the real benefit of going to this hybrid network or framework. So with this, these are the kind of results you're going to get. Are there any questions? It's about halfway through, so I just wanted to check. Sridhar, are there any questions to answer? Just checking.
Not yet, sir.
Okay, not yet. Okay, thank you. So I'll continue. So what you see here is an example of the speed up. So this is, we're trying to set up a matrix, an engineering matrix from boundary element. So on the left is if you were running on a single computer with an 8-core processor, you can see that you're getting approximately 7x speed up on 8-core. Okay, so this is not perfect, but not bad. On the right, you start seeing what happens when you have MPI across different machines. Because the interconnect is much slower on the cloud, you see you're only getting about 3x speed up on 4-core. And so you're slowing down compared to on the left. So this is a very common characteristic when you're trying to run on the cloud. So this is the setup stage when you're trying to set up a matrix. Now along with that will come the solve stage, which is once you have a matrix, you want to solve it by multiplying the matrix with vectors using iterative solver. Once again, you can see that with OpenMP, you're getting reasonable speed up. It's about 6.5 on 8-core. But when you do parallel right-hand side, which means just distributed solution with no communication, you're getting close to 7.5 speed up on 8-core. Because really it's inherently an embarrassingly parallel or an obviously parallel solution. You're just running multiple right-hand sides on different machines. So that gives you very close to ideal speed up on the right. So once again, what we're trying to say is depending on the operation, the cloud can give you very good speed up or minimal or modest speed up as on the left. So what we're seeing overall is this image that what you want is if you add more and more CPUs, 1 CPU, 2 CPU, 3 CPUs on the cloud, what you'd like to see is a speed up which looks like the yellow line, which is as you add more cores in each CPU or you add more CPUs, you just want a straight line in speed up. What you'll see because of Amdahl's law, typically if you don't do anything except just try to run your parallel code, you'll see the red line. You'll start seeing parallel, you'll start seeing good scalability, and then it's going to hit the Amdahl's law and level off. So you'll see this red line will level off. What the hybrid fine coarse-grained multithreading, which is what we've been showing so far, does is it constantly corrects itself. So this green line, it bends away from the yellow and then comes back again. So you tend to get much better speed up than with the red. You don't get close to yellow, but you can get very good overall speed ups close to 85 to 90% with this hybrid fine coarse multi-threading scheme. So this can be applied to many different engineering computations on the cloud, not just electromagnetics. Wherever you have matrix solutions, where you have multiple systems to solve, where you have multiple frequencies to solve. So as an example of what you can do in the cloud, this is showing a package simulation. So what we're trying to do here is extract the electrical behavior of a package, so-called S parameter or scattering parameter, which tells you how much signal goes through the package, how much gets reflected. So on the bottom left, you see S11. S11 is the reflection, and S12 is the transmission. So ideally, you want high transmission. So you want the green line to be high, and you want the reflection, the red line, to be low. You can see what happens as you increase frequency, the package starts behaving worse because there are more electromagnetic effects happening. So to simulate this for the package on the top left, which is a 10-layer package very commonly used in today's microprocessors, if you ran on 1 core, it took 900 minutes. If you run on 8 cores, it's 130 minutes. So quite a good speed up, you can see. But if you run on 125 machines, 8-core machines, it takes only 1.8 minutes on the cloud. So this is an example of the power of the cloud. So same code running on 1 core versus the cloud is 900 minutes versus 1.8 minutes. So it's a 450x speed up on 1,000 cores. Okay, in addition, there are some other bottlenecks like transferring the test case, computation, and results. So you can see even retrieving results takes 1 minute. So you are now coming to a different challenge, which is the data transfer becomes almost the same as computation. Okay, but that's a good problem to have. That means your computation is very fast. So this is an example of what you can do by running on the cloud. So I'm going to try and show you an animation of a backend running on a cloud, and please let me know if this is visible. Let's see if this is that visible. So you should be seeing a progress dialog which shows 18 different machines. So these are actually machines running on Amazon Web Services, and it's showing different performance, memory usage, disk read, network read, disk write, network writes on the machines. So what you're doing is you're running an electromagnetic simulation, but you're using the cloud in the back end. The front end is running on your machine, on a laptop, and the web services has been called at the back. And what you do at the end of it is retrieve the result automatically. Okay, so this is what happens when you're running the back end on the cloud. So what happens as a result of this? So this is just showing some diagnostics of how much scalability you get. And you can see different bars are active, which means you're in different parts of the algorithm. Right now it's using some memory but not doing any computation. So it's probably reading data from memory or writing it out. So now it's finishing up the writing, and now you've done. So this is a full result generated on the cloud. And I'll give you an example of what you were doing. So the problem you were looking at is really you have a chip sitting on a package on the left. And the question is how much electromagnetic interference is coming from the chip. This is a very important problem now because it's a question of how much noise is going from one chip to another. So if you have a biomedical system, will it pass your requirements? Or if you have electronic systems in a hybrid car, will they interfere with each other? So that's the problem which is solved. And once again, you can observe the data in many ways. So what this is showing is above the chip, how much radiation is there at different planes. So from this, you can check whether you are, for example, passing all the norms of FCC or federal commissions which look at radiation, for example. Okay, so this is what you can do very fast on the cloud as an example. So there are certain algorithms which are better suited for the cloud. The more levels of parallelism you can do, the better it is. For example, frequency domain versus time domain. Frequency domain is easier on the cloud. If you have multiple solutions to do with the same matrix, that's also better because that's dominated by soft time. So there are certain algorithms which will always be better suited for the cloud because the cloud is not a general purpose high performance computing environment. Moving on to another interesting topic which I wanted to just briefly mention is security. And as I mentioned, there are some actual issues and some perceived issues because you're outside your trustworthy environment of your own intranet. So customers tend to trust their own secure networks more than public clouds. And also, there's a challenge during the transit. What happens when you're sending data? So most large cloud providers do have standard security practices like 128-bit encryption and so on, which tends to be more secure than most internal compute centers. And so it's quite interesting that the standard security practice in cloud centers is sometimes stronger than that in internal centers. So it's a standard key pair-based 128-bit encryption is used. But there are still some challenges which I want to mention. These are things that researchers are working on now. So think of a class of problems where you need this scale of cloud solution because you want scale, speed, memory, but there is some sensitive data that you don't want to appear, that should not appear on the public cloud. What are examples of these? When drug companies pharmaceutical companies are trying to design drugs, they want to see how the drug will interact with the pathogen. So you're doing molecular dynamics, but you don't want necessarily the drug design to be available on the cloud because that might get accessed by someone else. Similarly, in the finance industry, you want to see how much risk you're carrying in your portfolio, but without divulging what your portfolio is. And in electronic design automation, you may want to do chip simulation or reliability without giving your IP about the chip layout and the chip technology on a public cloud. So these are class of problems where you need to do large computation, but you have some data you don't want, even by mistake, to be available on outside in the public. So here's the problem flow, and this is an open problem. I just want to mention it as things which are being worked on. Very interesting problem. On the left is a sensitive data sitting in a private node that passes through a network, which is the internet, creates some intermediate data. This is, for example, a boundary element matrix. And there's some computation done on the public cloud, and a solution is created. So that vertical line on the left is the line between the private node and the public cloud. So everything on the right is public. It's still secure, but it's in the public cloud, and everything on the left is private node. So what are how do you make this more secure? So people use encryption, right? You can use a key bit pair. So you encrypt your data, and then you transfer the encrypted data, which is the orange arrow, and then you decrypt the data once you're on the public cloud, and you do everything on the public cloud. So what you've done is you've added some layer of security on the transit, but there are still ways that you can break this encryption. For example, if I hack directly into the private node on the left, I can break your data. If I can steal the key, if I somehow get access to the key, then there's really no encryption. I can decrypt whenever I want. And finally, if I can hack into the cloud node itself, since everything is already decrypted, that's very easy to hack into as well, relatively speaking, because you don't have to do any key-based retrieval. So there are many places where a eavesdropper can break the encryption. So the idea of these methods, which are now being developed, are very interesting. These are called key-free one-way encoding, and the idea is, since you're already doing a lot of computation with the data on the left, why don't you use the computation as a way to do the actual encryption? So you're using the matrix methods as a way to encrypt. And so the idea is that, yes, you could still be hacked in the private node, but that just means that this is a challenge inside your own intranet, nothing to do with cloud computing. But from that point onwards, the data does not exist in any form which can be decrypted. It's already being converted to a different form through matrix computation. And so at no point to the right is it available, is the data which is on the left, the actual design data, is it available anywhere else? So the idea here is to use the computation you're going to do as a way to do an encryption. Okay, so that is what people are working on now. There are many ways to do this. You can use the same boundary element methods to actually do the compression and to do the encryption. But this is really an open problem right now, depending on your application. And it's very interesting because you don't have to rely on a key pair. You don't have to worry about someone losing that key or giving that key up. You're really using the physics of the problem or the engineering of the problem to do the encryption itself. Okay, so this is a sort of an open or a work in progress. Now, once you manage to run so many things on the cloud, the idea is it just about speed? I mean, if something took 1 minute, now it's taking 1 second, what is the benefit? So the real benefit is when you can do many solutions very quickly, because then you can do design, you can do multi-dimensional optimization, you can do parametrics. So that is really the reason to use something as fast as the cloud, if you can get things to be fast. So for example, going back to one of the engineering computations for electromagnetics, you want to generate not just values, but probability density functions or PDFs. So this tells you that if there's some manufacturing variability in your processes, how much is your answer at the end of your engineering computation going to change? So this requires a lot of computation, many different points or a Monte Carlo, and that is something you can do on the cloud as well, as we mentioned earlier. So for example, this is a computation you can do which is telling you how many components are electromagnetically good, which means in this case we're looking at an inductor. Now an inductor is good when it has a high quality factor, which means low resistance. And also you want the inductor to have a certain value in nanohenry. So all the red inductors are good inductors because they have a high quality factor and are in a certain range. Whereas the yellow and the red are all the inductors which were produced by a certain process. So this tells you how many are good. So this is really the magic number, the yield, which you can get just by simulation. So this is very valuable because normally trying to run a simulation like this would take you many days or even months. But again, using enough nodes on the cloud, you don't need high speed interconnect, or you just need a lot of nodes which can be independent, and that gives you the ability to do yield modeling. With that, you can do other things like optimize geometries. On the left is a package for an electronic system, and you're trying to reduce the return loss, which means how much reflection happens when you send a signal. So by changing various parameters, you can play with these return losses until you're happy. And eventually what you can do is what's called the Pareto-Front, which is I want to optimize for many things at the same time. So I want to optimize for crosstalk, which means how much noise there is. I want very low noise. And I also want very low return loss, which means very low reflections. So I want my signal to go from point A to point B without being reflected, and also without being picked up by any other signal path, which is crosstalk. So what this front on the right generates is all possible solutions. So you see this double convex shape on the bottom right, like sort of two curves on the bottom left of the curve. Any point on that bottom curve is called a Pareto optimal point. All of these are the best points you can get. And again, to generate this kind of curve, you need thousands of simulations. You're able to do that in just 5 minutes on the cloud. So these are really the emerging benefits of the cloud. It's not just faster simulation, but trying to do design on the cloud with these fast simulation methods. So that actually brings me to my last slide, which says that the reason we are trying to use the cloud is to do large-scale engineering simulations in an elastic manner, in a way that you pick the nodes when you want them. Because due to economies of scale, cloud computing is continuing to grow. Cloud computing is never as ideal as a fine-grained, high-performance compute cluster. So these very expensive supercomputing clusters will remain important, but so HPC and high-end clients will continue to thrive, but as cloud continues to grow, the need for HPC will go lower and lower because you'll have more nodes with faster interconnect. For any given task, you're going to have slower interconnect on the cloud than on HPC. So the way to tackle that is to have hybrid parallelization, which is more and more layers of parallelization, not just multi-core, but MPI and distributed. So that is dependent on your application. There are certain applications where you can do more levels of parallelization. Those are better benefits for the cloud. The most exciting part of running on the cloud is that in the very near future, we should be able to do many engineering designs in real time. Essentially, you will be able to draw an engineering structure, change it, and see the impact on the engineering. For example, whether it's stress, whether you're looking at fluid flow and pressure, whether you're looking at electromagnetics or circuit behavior. In real time, you'll be able to move these structures around and see the effect immediately without having to wait for it. And that, I think, is the most exciting part of running on the cloud. And eventually, you hopefully will be able to create a community which will use common tools and benchmarks, which is really the aim of running everything on the cloud. So we have one place where we can create a large repository of these very large-scale codes. So I think that's my last slide. I'll come to end, and I'm happy to answer any questions. Thank you.
Shall I read out the questions?
Yes, please.
Is it a coincidence that you happen to select parallelizable matrix problems, or is it that cloud is especially suitable for parallel computations?
Yes, that's a very good question. So what I'm trying to pick is which kind of computations is the cloud good for. The fact that you have many cores means that it should be good for parallel computation because you can bring up as many cores. But the challenge is that these cores are not connected with high-speed interconnect. So not every parallel problem is well suited to the cloud. So what we're trying to pick is that class of parallel problems which is well suited. So that's where these matrix computations come up. So whenever you have large matrix computations, they are perfectly suited for the cloud. So good question.
You said private node hacking is possible in both ways. Can you explain it again?
Okay, so if I go back to just 1 second. Can you see the slide? Just checking the security challenges slide.
Yes.
Okay. Okay, so if I go back a couple of steps here. So if you look at when you're trying to encrypt, then before the encryption, so let's say you're sitting in your organization's intranet and someone hacks in there, before the encryption step, that is one place where your data could be stolen. So that's an example of what will happen with encryption. Now, if you use the other technique, which is the key-free one-way encoding, you're still having to do one intermediate computation, which is the orange square. But before that, you still have all your data in non-encrypted form sitting on your private node. So it's equally likely that if someone breaks in, that they will get access to that. So there's no added security inside the private node. So both these steps are equally secure or insecure inside the private node.
How can cloud encryption be used in smart card-based authentication?
Interesting. That's That's a very interesting question. I'm trying to think of the fact that most of the time, if you're using a key bit pair, which is what is very commonly used, which is what is done here, the presence of the cloud really doesn't benefit you, because this can be done anytime you have two networks connected. You just connect them by 128-bit encryption. However, what you're saying now is if you are able to use this one-way encoding on the smart card, there may actually be a way. Now the question is, though, that somehow that has to be more than just a key. There has to be some computation which is done on the smart card. So it really depends on what you're storing on the smart card. I don't have a complete answer, because if it's just a key you're trying to, or a small amount of data you're trying to protect, then you have to do it in this way typically by a key pair. So there may be a matrix formulation for that, but again, this is a good question. I don't have a full answer for this one.
What are the other security open challenges?
So really, the open challenges here are security in transit, which is really the orange things you're seeing here. And the other part is security on the cloud itself. So which is, for example, as we said here, if you go to the key way of encrypting, then once you're on the cloud, unless you do some encryption, you can really, if you hack into the cloud node, you can get all the data. So what people are now doing is making sure that everything remains encrypted even on the cloud. The problem there is there's actually an efficiency step, because you have to decrypt and encrypt every time. So there's an actual effect on the performance of your algorithm. So that is still a challenge, which is how do I store things in a secure way on the cloud while making sure I don't have a hit on performance when I have to do many computations.
How can we test the security of a cloud? If we come with a new algorithm, is there any simulation using which the security tests can be performed?
That's a brilliant question. Very good question. And I would say the answer is no. If you have a new algorithm, there is no way to prove whether it is secure or not. You can do a lot of testing. That is, you can simulate how certain attacks may happen, and so, but you can never prove that you exhausted all possible options or all possible ways of attacking. So that's a very good question, but I think that it's really an open problem, which is how do I know something is secure? For example, if one of the cloud nodes you are trying to access has been affected, this is an open problem. How do you know it's been affected? That is, how do I know that a certain cloud node should not be trusted? And that's really a related problem to what you're saying, and it's still an open problem.
If I wish to try a problem on a cloud, where do I get an account number and login procedure?
So the easiest way to get that is through the Amazon Web Services. So if you have an Amazon account, I think that can be set up very quickly. And I think it's just credit card based. So if you have an access, then they will charge you by the hour. And the costs are very low. In dollars, it's probably $1 or $2 an hour for per day for the smallest machines. And so you can test out on Amazon EC2. I would say out of all the available cloud computing, the Amazon EC2 is the easiest to get an account up and running. It can take you less than a day to get started on working on the cloud.
Is cloud computing useful for learning purposes, and how?
That's again depends on what you mean by learning. If you mean learning actual computation, I would say definitely, because it lets you do things like understanding parallel computation and scaling. If it's more about education, then again, it's a way to distribute as well. So I think it's really a paradigm which is for both learning and teaching. So yes, I would say yes.
Does cloud computing reduce cost?
Yes. So the short answer is that's really the reason why people are moving to the cloud is, for example, if your core expertise of your company is in creating a product, then your core expertise may not be in managing a data center. So instead of you having to requisition hardware by IT manage power, if you're letting someone else do that who has economies of scale like Amazon, and you pay a small premium for that, which is much less than what you'd pay if you were trying to do it in-house. So really the number one driver for cloud is cost. Along with reliability is cost. So yes, you do get large savings in as you scale your application, you get large savings if you run on the cloud.
What is the minimum investment for a cloud?
So in terms of, again, interesting question. So in terms of to get started, the cloud is really elastic, which means you can really say, I want to spend very small amount of money, maybe 100 rupees or $2 on and to test cloud. So you can really start as low as you want. And I believe the smallest instances on Amazon are like 0.18, like 18 cents or so. So you can really, your investment can be as small as you want, and that's one of the benefits. You don't have to buy a machine and power and IT. And then you can make it, of course, you can spend as much as you want depending on number of cores, but you can start very close to zero and scale up as you want more needs.
If once we keep our data in a cloud and avoid using hardware, we may avoid cost of buying it, but we should pay the whole we use the cloud. Otherwise, with our hardware, once we buy it, we can use it forever.
Mm-hmm.
Let's see what he says.
Yes, yeah, I think I see what you're saying. So there is a cost to storing your software and your data on the cloud. So this is charged by the second. But again, I think the argument is that even if you bought your hardware yourself, there's still cost, because one, there was capital cost in buying it. Two, no hardware lasts very long, right? So you have a time scale of that. And there's power usage as well as management in terms of IT. So all those costs are still there. And compared to that, the cost of per gigabyte of storage on the cloud is very, very small. So once again, once your data is large enough, even if you store in the cloud, overall you'll come out positive in terms of total cost.
How is software deployed on the cloud secured?
So there are licensing schemes now which are cloud-based, which have to be, so there's no company doing it, it has to be done by each individual company. So normally, again, you do this 128-bit key pair encryption, and that's the most common way of doing it. There is still an open problem as to how to license, for example, the equivalent of FlexLM, which is a very standard license daemon. There is no equivalent on the cloud. So this is still a problem for the kind of software which you want to secure on the cloud. And that's why a lot of software which is running on the cloud, the real IP is in the data or in the way it's used or in the sort of the social network or the interaction of the pieces with many people. Okay, so really the fact that you want to put high cost engineering software on the cloud which you're worried that someone may copy, that's still an open challenge. The licensing on the cloud is still not fully coming.
Can a cloud service provider pirate the application deployed?
Very good question. So every cloud provider actually makes sure that the only person who can access that particular machine is the person who actually started up the machine. And this is guaranteed by encryption. So the cloud provider does not have access to any of the data which is available. So there is no way. That's one thing. And secondly, once you turn off your application, this is a virtual machine and everything is gone. All the data, all the software is actually gone, and even any hard disks are completely wiped. So the data only stays as long as you're running it, and during the time it's running, only you have access to that machine. And so it's very rare that you expect that a well-managed cloud provider will be able to hack or steal code.
How can I use some real-time system algorithm like EDF and RMA scheduling algorithms?
I don't know if they're directly applicable on the cloud, so I'm not sure because they have some latency challenges. So I'm not sure if the cloud will allow the right. I don't know enough about them to be able to answer how latency affects them. So sorry, I don't know the answer to that.
How can we ensure access control mechanism in a cloud which consists of multiple security domains?
Very good question. So this is sort of a multi-cloud environment. So this is where you have there are different ways to do it. So when Amazon does virtualization, they actually have multiple multiplexing happening on the same machine, but it's as secure as, for example, Unix. So it's multi-user in the sense of a multi-user operating system, and so that's very commonly done on Amazon. When you're trying to mix clouds, so let's say you're running part of the solution on one cloud provider and one part on another cloud provider, then it's really up to you to manage the interchange. So that's a more challenging problem, and that's why people tend not to do that right now. But that may happen in the near future when you want to move across different domains. How do you actually move from one cloud to another seamlessly, or add one cloud node in one cloud provider and remove from another cloud provider? That is yet to be determined. It's very rarely used right now.
What are the costs of hosting a website of 20 GB size on cloud?
So let me see. So 20 GB, I'm just trying to do the math here on S3. I think it's going to be on the order of a few dollars a month, so around $5 a month or so. I can check the exact number, but it's definitely less than $10 a month. Plus, the benefit is that data is available to you to do other things. So if you want to do analytics, if you want to have a high, if you want to do computation on that data, so for example, analytics on Amazon, you can do that for free. The bandwidth between EC2 and the storage S3 is free. So you can move a lot of data between different machines and your web server for free as well. Okay, so that's an interesting benefit of being on the cloud, that you can do computation and web service together for the same cost. So I would say a few dollars a month, but I have to dig in more deeply to tell you exact numbers.
So we're almost out of time. Do you have time for a few more questions?
Sure, I have yeah.
Okay. How analysis of algorithm related to cloud computing can be done?
So the two things that you have to figure out when you're trying to analyze algorithms in the cloud, one is how parallelizable is your algorithm. So really this goes back to what are called directed acyclic graphs, or DAGs, which is given an algorithm, how parallel can you make it. The other part is the latency. So as you break a problem into multiple parts, you also have to collect the data back. And this is more challenging because the latency is not only high, it's a random number when you have in your cloud machines, because the bandwidths can change depending on congestion. You may have two cores which are very far away and two more which are very near. So you have a stochastic distribution of bandwidth and of latency. So that really is where you have to have bounds in your algorithm, which says what is the worst case latency and therefore the worst case performance. So again, two steps: how much you can parallelize, and then what is your worst case behavior when you have latency of a given bound.
Are encryption algorithms being used in clouds?
Yes. So again, the 128-bit key pair is very commonly used. RSA and other key bit pairs are used very, very commonly. And it's done very securely so that only the requisitioner, the person who's paid them money to start the computer, has the only one who has the access, not the user, meaning the application user who's running your software, and not the cloud provider. So yes, this is very commonly done.
Where does parallelizing of data take place in a cloud?
So the parallelizing of data is done manually in the sense that there are two things. So one is, so Google has a set of libraries, or IBM as well, called Hadoop, which tries to do distributed computing, which is not exactly parallel, but it farms out data. This is done automatically. So for example, if you're repeating the same computation for many times, this can be done automatically. The final level parallelization is done on a head node. So you have a master node which is sitting on the cloud. And just like a scientific computing cluster, this then has slave nodes which are also sitting on the cloud. So that's where the parallel farming out or MPI is done between the master node and the slave nodes. And they're all in the cloud.
Is group key authentication possible in cloud environment?
Yes, absolutely. So that is used. The only question again is latency, but other than that, it works as well as in normal systems.
How is our data protected when cloud disaster occurs?
Excellent question. So there's many levels of redundancy. So what, depending on which cloud provider you talk to, they are able to replicate an entire data center. And a data center has millions of nodes. So even if an entire data center goes down, they're able to replicate the entire data center, basically copy the entire data center before there's an exact copy made. So essentially there's a full redundancy available at all times. Now if two data centers go down simultaneously, there's a chance that you can lose your data. That's the worst case when you have sort of the mirror data center and the actual data center both going down at the same time, then there's a possibility of losing data.
How can we relate cloud computing and real-time system? Hello? Hello? Hello?
Yeah.
Hello, sir, can you hear me?
Yes, Sridhar, I can hear you.
Yeah. Can we schedule backups on our data which is on the cloud?
Yes, so you can back up data. You can do this again. You can do it manually. You can do it, in a standard scheduled manner to other nodes. There are two kinds of nodes you can have. Those which you only run when you're running some computation, and then they shut off, and you have no access to that data. Or you can have, by paying a little more, you can have a persistent node, which essentially you own and is sitting in the cloud. And you can copy a lot of data onto that or from that onto other nodes as well. So yes, you can schedule backups of all your data on the cloud.
Are there any tools we can use for research on cloud computing or any other simulation tools?
There's so if you go to Amazon, for example, what people have done is created what's called a public instance. A public instance is a kind of machine including all software libraries. So for example, if you're interested in running software called Python or a language called Python, which is very popular nowadays as scientific computing and testing language, then you can get instances which when you start the computer, it automatically has Python. Similarly, you can get other scientific computing libraries already existing on there. A lot of metrics are there. It will tell you how things parallelize, how much latency, how much bandwidth is there. So a lot of measurement tools exist as well. Other than that, there are more tools coming from universities. For example, there's a virtual cluster called a star cluster, which lets you do things like MPI and HPC programming on cloud machines. So you can open up this instance called a star cluster. So there are many of these tools which are coming online on different cloud vendors.
Is there any speed difference while accessing an application from cloud to my local machine?
So there's one class of applications where this is very visible, and that is 3D rendering. So for example, if you're playing a complicated game, with a lot of graphics, or you're trying to do, for example, AutoCAD or rendering of objects, unless the rendering is done locally with some compressed data being passed, if you're trying to render everything on the cloud and then visualize on your machine, you can see delays. That is one example where it's very important to do this correctly. As an example, you have streaming video. Netflix is an example of streaming video. Netflix does run on the cloud. So you can see there's very little latency if you're doing it properly. So a lot of effort done on the local machine in rendering video properly. But if it's not done, if you just try to run the same simulation and set up an X server, then you'll see very, very slow response when you run the cloud.
Last two questions. What are the prospects of hacking in Amazon EC2?
Good question, very good question. I think it's about the same as hacking into any high security data. So as you know, Amazon also does a lot of e-commerce. So they are very, very careful about security because there's so much credit card data and so much information. So they use the same principles in cloud computing as well. So I would say it's very low probability, but it can still be done, of course. But I would say it's as difficult as any other very high e-commerce or banking site to try to break into.
The last question is, when can we use private and public cloud?
That's again a very good question. So private cloud is a cloud-like software architecture and hardware architecture, but sitting inside a domain which you own. So for example, if I am IBM, I might say I want to run Amazon EC2-like software on my machines, and so that's private cloud. So private cloud is used a lot when, one, you have a lot of your own machines and very good data centers where you already have economies of scale, and two, you have a real need, or whether it's legal or technical, that no data should ever go outside your domain. And so if you're a large company with a lot of resources and a lot of data which you don't want to go out, then private cloud becomes a very good option.
Thank you very much, Dr. Jandhyala. If there are some questions which are missed out, is it okay if the attendees email you?
Absolutely, I'll be happy to answer those. And I'd like to thank the attendees for attending this, and thanks to you for setting it up.
Thank you, sir. Thank you very much.
Thank you. Bye-bye.
Bye.